Okay, well, thanks for attending this workshop. Basically, it's going to be a very basic introduction to what is GPU computing. We have very ambitious plans for the next release of Mathematica. Basically, we understand that programming in either CUDA or OpenCL requires a little bit of training, not just for people that know C programming or C++ programming, but also it requires, in particular for optimization of the code, it requires a little bit of knowledge exactly how the parameters that you pass or the sizes of the arrays that you pass, they are going to affect the performance and of your computation. So all of that, the goal for the next release is to abstract all of that as much as possible. But for this workshop, basically is an introduction. The material is mainly the same that you can find in the documentation. The idea of having this workshop is to give you just in just one notebook some very quick examples that you can start building on top of. Okay, so basically, everything for CUDA and OpenCL programming is built on the version 8 features. As it was already mentioned before, basically there are three basic components for the GPU support. One is the library link, Symbolic C, and the compiler. Library link has been used very, very widely since version 8 came out. Yesterday there was a presentation on how to link MATLAB into Mathematica using precisely this technology of library link. If you're familiar with MATLink you will really, and you have used MATLink, well, you may be familiar that there is still some overhead that you need to know before you start writing your functions using MATLink. Library link is a much more friendly way of connecting your own libraries, to Mathematica. Symbolic C, basically, it allows us to abstract the programming language into a version of Mathematica that basically later on you can use that abstraction to generate code for as many programming languages as you want. So in our case, basically, we use these two components to basically generate code that can be compiled either for CUDA or for OpenCL. And the compiler is basically a way of how to process the abstract language that Symbolic C generates, and how to generate executables based on the platform on which you are running. So GPU programming, basically right now the APIs for GPU programming are basically CUDA and OpenCL. So basically CUDA is the more broad this is the one that is being used more frequently since it has been around since 2007. It's proprietary from NVIDIA. And some of the features is that it's very similar to C++ features with respect to template support. It's very mature in the sense that there are a lot of numerical libraries for CUDA. We get that question a lot. What should I use? Should I use CUDA or should I use OpenCL? Well, and the answer is that, well, basically, if your application requires some high-level numerical methods, at this moment, basically, you should use CUDA since it provides already several numerical libraries. Metrics, some versions of LAPACK, and they are supporting sparse matrices and so on. So basically, if you are very invested into building on top of numerical methods for linear algebra, you should use right now CUDA because it already has the libraries. So in your system, basically, the way that you detect if you have a CUDA support, basically you run this command, needs CUDA link that loads the package, and then you run this function CUDA-Q. In this case, telling me, yes, you have a video card that is CUDA enabled. For OpenCL, basically, this is an open standard. It's been developed by Kronos, the same people that develop OpenGL. And basically, this API is supported by Apple, for the Macs, NVIDIA's AMD ATI. Okay, the language is very C-like. Okay, this doesn't have the C++ template support that CUDA has. Okay, and basically the first stable implementation was in the middle of 2009. Okay, they have been promising us to have an implementation way before this year, but it wasn't until this year when something came out finally. It was not very stable, and finally last year they started coming up with something that was more usable. Actually, just as people that tried, when we released version 8 and people tried to use OpenCL, they found out that it was not working. One of the reasons is that just after we released, like a few weeks after we released version 8, AMD, they changed the names of the libraries that they distribute with their ATI SDK. Okay, so the functionality was the same, that they just rename all the names. Since they got rid of the name ATI to be now AMD, okay, they renamed the libraries, and that broke basically all the OpenCL support that we have. So now we are working more closely with the people from AMD, okay, just to make sure that they don't make changes that we are not aware of. Okay, and the same thing, you load the OpenCL package, and then you check that your card supports OpenCL. OpenCL is supported by both by NVIDIA and by AMD cards, okay, and yeah, by the Mac systems. You can get some of the information on your system, basically which kind of video card you have, which kind of support. In this case, you run system information, and then you have all this information about your system. Okay, in particular, you go to links, you can see that you have here an entry for CUDA, and it tells me basically which video card I have, okay, how much memory I have in that video card, the number of cores that it supports, and in this case, this card supports double precision. Okay, I have one more for OpenCL, okay, and then here is telling me the same properties but for OpenCL. Okay, so this is one of the first things that you do when you want to check if your laptop is CUDA capable, or if you have a system that is able to run CUDA or OpenCL. If they don't support it, basically these two are going to be empty. If you want to get more specific information about the CUDA hardware that you have, you can run just use CUDA information. In this case, you can see that we have a list with the number of the device. In this case, is 1. If you have one of the very fancy workstations that have multiple GPUs on them, you are going to have multiple entries here in the CUDA information. Okay, you have a system with 4 GPUs, you are going to have one entry for 1, 2, 3, and 4. The same thing for OpenCL. In OpenCL, actually, yeah, in OpenCL you are going to have this basically the same information that you can query. So these are just the preliminaries. Another thing is that if you are going to be using CUDA and you are going to be compiling your own programs in CUDA, you need a C compiler. Okay, we support several compilers. We support the Visual Studio, GCC, and I don't know. Here we support the 2005, the 2008, and the 2010 Visual Studios. And this is the NVIDIA compiler, basically. This is what gets installed when you upload the data packlet for CUDA. Basically, what it does is that it downloads the CUDA toolkit from our servers, and that provides precisely this NVIDIA compiler. That is what is going to compile the CUDA programs. So basically, how does a CUDA program look like? Basically, we start with this. Basically, we have a list of values, okay, from 1, 2, 3 until 224. Okay, and suppose that you want to use basically add the number 2 to each one of those entries. Okay, a C program will look like this. Okay, basically you just iterate over all the indices on that array. Okay, and you just increase the value by 2. So the CUDA program is going to look like this. So they are basically the same. They are very similar. The main difference are that these identifiers here, these types, okay, this global basically is telling me that this is a function that is going to run in the GPU, okay, and then we have to basically compute manually which is the address in the array that we are referring to. So, but this is the, you can see that they are very similar in that sense. So the basic structure of a CUDA program, okay, you have to use, you give a name, okay, you give the arguments to that function, okay, and if the signature of the function in my CUDA program looks like this, the way of calling it in Mathematica using CUDA function load basically is almost like almost like one-on-one mapping between the signature of the function and the way that you call CUDA function load. You need to specify the source code that you are going to be compiling, okay, the name of the function that you are going to be invoking from this CUDA program, okay, and then you need to list which kind of arguments is going to use. The syntax that we are using for this is compatible with the compile command. So for people that are familiar with how compile works in Mathematica, they are not going to have any problems understanding this syntax on how to call the CUDA and OpenCL programs. So yeah, so in this example, this is the prototype that we have for this function at2 in CUDA, and this is how you call that function directly in Mathematica. For OpenCL, you can see that the code is very, very similar. Okay, actually, if you compare the code in OpenCL, okay, and the code in CUDA, you will notice that basically they are the same, and basically you can do basically a translation between one and the other. Okay, the way of that you call it is very similar. Okay, I'm not going to go through all of this because basically it's very basic in that sense. But basically what you should be aware is that writing a program in CUDA or OpenCL, basically they involve almost the same work, and you can translate from CUDA to OpenCL just by following this substitution table. Okay, there are of course a lot of other features like how to synchronize threads and how to put locks on memory and things like that, that of course they are a little bit different, okay, between OpenCL and CUDA. But the basic, if you want to do a very simple translation between one and the other, basically you have to follow a table like this. It's very straightforward. Why you want to program in CUDA Link and OpenCL? Well, Abdul already mentioned, okay, well, one of the main reasons that most people think of when they set up GPU is that, okay, I want my programs to run faster. Okay, if you are not using a system like Mathematica that generates CUDA or OpenCL code, basically, if you start looking at the documentation that NVIDIA provides or the documentation that OpenCL provides, you are going to spend several days just going through all the things that you need to set up just before running your kernel, okay? You need to learn how to allocate memory in the GPU, how to move memory from the CPU to the GPU, how to configure how your programs are going to be launched in the GPU, okay? How you need to group them, okay? And then you need to run the kernel that you are going to be running, okay? This is your CUDA kernel code. And then you have to go back, okay? You have to wait for all the threads to finish, okay? Just wait that all the data that is being computed is at the same point. And then once that you know that the computation is done, then you need to move back. You need to move back all that data from the GPU, move it back to the CPU. And mainly, a lot of the benchmarks that people publish when they said, okay, I implemented this using GPU, using a GPU, using CUDA or OpenCL, they report the timing, basically only the timing in this part. Okay, it's very common that they never report the whole process. That's why they report speed ups of 100 or even higher. Okay, but when you factor in the cost of transferring memory between the CPU and the GPU, okay, you see that that's the real bottleneck. That's what really slows down all the gain that you could get using the GPU. That's where you lose all that speed up. So there really is a trade-off. Okay, for certain sizes of problems, it's better just to run it in the CPU. It's not really worth trying to run it on the GPU. But if you're going to be running a process that really requires thousands or hundreds of thousands of computations, okay, and if you are careful managing the memory, transferring only once and try to reuse that memory as much as possible, leave it in the GPUs and run several kernels, run several computations reusing what is already in the GPU, and try to avoid the transfers back as much as possible. That's when you start getting a lot of gain, and that's precisely what makes a good CUDA program, what makes a CUDA or OpenCL program very good. Okay, because all that optimization, that's what really takes all the time in implementing. So with CUDA link and OpenCL link, basically you don't have to worry about any of these steps. All you need to worry is about writing your CUDA kernel code. Okay, so what we offer is basically an abstraction of all the setup and all the finishing, basically. So basically you can prototype you can prototype, okay, then you can run your CUDA kernel, and then you can test the results that you get. So that's what this system does. Another of the advantages of using this system is that basically we provide a platform-independent environment. Okay, we can use, and we have defined all these pragmas, we have defined all this, that basically it allows you to write programs that adapt to the hardware that you are running your program on. Okay, so you can write a CUDA or OpenCL program, and by using some keywords, basically you can make sure that program is going to run on the hardware that is very low, like consumer GPU cards, okay, or very high-end cards. You can also make it, you can write it in such a way that it can run in either ATI or, well, AMD or NVIDIA cards. And that's precisely all what Abdul was mentioning before, that it should be transparent, and that's something that Abdul is working very hard for the next release. Okay, that basically you don't have to worry about any of that setup. Everything is going to be done in the background. And now, once that you are writing a CUDA or OpenCL kernel, basically loading that into Mathematica, they use a very similar syntax. We have a CUDA function load and an OpenCL function load, and they follow exactly the same syntax. Okay, so basically all you need to do between one and the other is just to change CUDA for OpenCL, and then you can reuse your code for both. So this is a more elaborate example of how you can do some image processing. Okay, this is a kernel code that a CUDA. No, this is an OpenCL program that basically does image adjust. Okay, so and here we see that we can load it using this OpenCL function. Okay, and then we can basically run our kernel on an image. Okay, so look here that I am already using the Mathematica syntax to run. Once that I load that function, okay, as a Mathematica function, I can use that function directly into Mathematica as any other system function. For example, in this case, I am just using the Mathematica syntax in this table, and I'm applying different values, and all the computation in this case is being done on the GPU using OpenCL. So here we have another example. Yeah. Yeah. So as you can see, when you're trying to solve a problem, okay, and you want to start involving the GPU, either CUDA or OpenCL, this gives you the advantage that you can prototype only the parts that are needed, okay, on CUDA or OpenCL, and do the rest of the processing using all the Mathematica functionality. So this is another example. This is the game of life. Okay. This is how you load that function. Okay, so we start with an initial states. Okay, and then here we have dynamic. Okay, to refresh these values. Yeah. So all of this is being run on the GPU. Basically, all of these pixel values, basically, they are being updated in the running the GPU on them. Again, the idea of this workshop is that you can start playing with some examples, some very simple examples, and you can start basically trying to do a little bit more of more elaborate examples with them. For when you ask about the parallelization using GPUs, in Mathematica 8 there is a when you call one of the functions, there is a variable that is called kernel ID. In this case, since I only have, since I only have, the IDs start from 0. Okay, since I only have one GPU card, okay, in this case, I only have one ID. Okay, if I have multiple GPU cards, each card can be assigned a kernel ID of 0, 1, 2, or 3, and so on. So when you use, for in this case, when you try to parallelize a program using Mathematica, basically you can run, okay, and then you can specify. You can run your CUDA or OpenCL programs, and you can specify on which device it's going to be running. Okay, in this case, well, it's going to be, it's supposed to be 0 here. Okay, but since no, okay. What happened, Abdul? It's supposed to be 1, yeah. Okay. Okay, yeah. So the IDs goes from 1, 2, 3, and 4, yeah. We do the mapping internally to do that. So if I had multiple GPU cards, basically I could parallelize on the different GPUs this computation. Yeah. So another example, at the beginning when people start working with the GPU, it's a little bit tricky to understand exactly what the different terminology is. For example, grids, what's a grid, what's a block, and what's a thread. So basically, in this case, we visualize all the processors in the GPU, okay, as this array. This array basically is what is called a grid. Okay, but each basically, we organize them into what is called blocks. Okay, and then inside of each block, I have different threads. Okay, so this is basically just a visual representation of how you are partitioning all the cores that you have on the GPU. So when you start writing some programs in OpenCL or GL, you have these variables, okay? Thread ID X and block ID X and block dimension X. And basically, if you want to start understanding exactly what these variables mean, okay, so you can just use this program that basically, in this case, I am just saving the value of the thread ID in X here. Okay, I get the result, and you can see exactly. I'm saying, okay, I want to subdivide all my processors into blocks of length 16. Okay, so you can see here we have from 0 to 15. So I have 16 on each block. Okay, and then you can see that each one of those is going to be saving the thread ID, and that's what you get this pattern. For two-dimensional case, here in this case we are taking only the block ID X, and then when I run this, you can see exactly what part of the array is being processed by each one of these block IDs. So for example, if here I change this and I said, okay, add to this at the block ID next, okay, and then I run it, okay, then I get a different pattern. Okay, so this allows you to very quickly start experimenting and try to understand exactly how the computation is being distributed through the different threads in the GPU. And then, yeah, this is the OpenCL version. You can see that the code is basically the same. It's very similar. Yeah, and in this case, I'm doing two things in the semikernel. Okay, in one of the arrays, I'm saving the index and x, and in the other one, I'm sending the index and on y. Okay, that's what I have these patterns. So for people that are interested, for example, in writing their own filters for image processing, because this is an example that basically computes a median filter. Okay, so we use the image processing capabilities in Mathematica to compute the actual median filter of that image. So which is good in this case to eliminate all the noise. This kind of noise. They call it sandpaper noise. Okay, and this is the median filter, what it will do. So how can we implement something similar using the CUDA? Okay, so in this case, the program that will do that is in reality is very simple. This is going to be the name of my kernel. Okay, and you see here that I am the output of the results of the output is going to be the call of this function median. Okay, and this function median is this function here. Okay, you can see that here I have two different keywords here. One is global, which is that this is a function that is callable from the CPU, but it's going to be running in the GPU. And this is telling me that this function can only be called from the device, from the GPU. This is not a function that I can call from the CPU. So basically, this is a local to the GPU function only. So, okay, I define this is my CUDA program. Okay, so with this, I load that function into Mathematica. It gives me back that function. And then basically what I'm going to do is I'm going to apply this filter. Basically first, okay. Here it's telling me that I didn't pass the correct values. Okay, so I apply the filter in the horizontal direction. Okay, then I rotate the image. Okay, and then I apply the same filter now on the, it's going to be on the vertical dimension. Okay, and then I flip it back to how it was, and this is the result. So, and then we can compare basically the original image with the, this is what Mathematica generates, and this is the filter that we just wrote using this method. In this case, you can see that you can start prototyping parts of your filter. Writing how to rotate an image, okay, it can be a little more complicated in CUDA, or you will have to basically, instead of computing the median of 3 values, okay, basically, if you want to do all in once, basically you will have to compute the median of 9 values. Okay, you have a 3 by 3 kernel, and you will have to compute the median of that value. And you can see the rest is just identifying exactly when you run this in one of the threads. Basically, you need to identify to which index in the arrays you are located. This is what these 3 lines do. Okay, and then I basically compute the 3 values x, y, and z. So I compute the value in the center, and I compute the value before, and then I compute the value after. Notice that you have to be careful identifying precisely that you are not running out of bounds. Okay, you need to identify that the memory the memory references are between the bounds of the data. So basically, all this checking, you need to check all the parameters, and this is something that you need to do manually. And again, all of this is going to be abstracted into the next release when we have a final version of the CUDA compile, or the compilation method for CUDA. So something that you can try to do later, okay, is how can I modify this, okay, to run instead of the median, use the mean, or even how to replace it to pass your own convolution kernel, okay, for the image processing. So, but this is basically, it gives you a template of something that you can start building on top of, and it gives you a start on how to write. In this notebook, yeah, these are very simple tasks. So, yeah, in this case, yeah, how you can change that to compute the median, and the rest of the code is basically the same. Okay, another is, okay, how can I write this in OpenCL? This example is in CUDA. Okay, so by following the table that I showed before, basically you can translate these programs, okay, and then you can write it to use OpenCL. So you don't have a card that supports CUDA, then you can try to port this to use OpenCL. So another very quick example is basically for finite difference. This is something that a lot of people need to do. Basically, they want to solve their own linear solvers or the solvers and so on. So in Mathematica, it's very simple. We can just use the derivative, or we can try to do a discrete version just by sampling and then finding the differences. And this is what you will get in Mathematica. Okay, but yeah, and then here we just compare what this method of sampling does compared with the Mathematica implementation. So, but now how do we do something like this in CUDA? Okay, so basically we can use some of these finite difference schemes. Okay, in this case is the backward difference. This is a very simple approximation. Okay, basically I'm just, I check that I am not out of bounds from my data. I'm computing in the kernel, I'm computing that function. Okay, which since CUDA supports the tangent, okay, we can compute it directly there, and we just do a finite difference. Okay, yeah, and these are our results. I'm not doing any scaling or anything in particular here. I'm just doing a very quick prototyping of this. Well, this works for this function tangent of f. But what if I have a more exotic function that basically is not supported into the CUDA or OpenCL? Well, then in that case, basically I just send the samples. Yeah, so here we have another example where basically part of the input to the CUDA function is a sample of the function values. Okay. So basically, this will be a very quick prototyping of how I can write a more general finite difference solver. So again, this is a task, how to implement a second order finite difference. Okay, so this is the scheme that you are going to be using. Yeah, the solution is given. So basically, I just need to replace that for that. So this is something that you can start building on top of for more complex examples. Okay, another example is this iterative system. Okay, the Julia said basically you have this rational function, and basically here you can see what the real and imaginary part are of this function. Okay, and then here basically you just do an iteration. Here you define the values of x and y based on this complex expand for this rational function here, and basically you just do the iterative, okay, and then you assign colors based on what the ratio of convergence. So I can run this function. Something else that you can see here, another feature is this option that is called defines. You can see that you can pass define values to your programs. Okay, in this case, the max iterations. Max iterations is a variable that I have defined here. I can say bailout, and I set out the value of the bailout value and the sum value. Okay, so you can see that this mechanism allows you to basically programmatically generate GPU programs. Okay, so you can generate these kernels and run programs, and you can really optimize them based on the problem that you are trying to solve. Here I don't have to worry about how do I write a nice interface to display it. I am using manipulate, and I'm using relief plot, okay? And I basically just getting the values, okay, from calling the function. Here, okay, Julia calculate. Here you allocate the memory once, okay, and then basically you computed this, and you only so you can see that is very yeah. So all of this is being run in the GPU. That's why it's so responsive for the interaction. If you try to write this using just a standard Mathematica, or you will see that it will be very slow, the generation of this. So again, here we have another task. Is compute the Ulises for this iteration function. Okay, you have a hint that basically you can use. Well, yeah, you want to figure out what's the real and imaginary parts. Okay, so what I will have to do, okay, to run that is basically use this output to replace it somewhere here, and the rest is exactly the same. So yeah, you have the solution. Here we make that substitution. The rest is exactly the same. I haven't changed anything. Yeah, and then you have a different. You have a Julia set of a different rational function. So, of course, when you start writing this from scratch, it's very common that you can make a lot of mistakes. With you miss a semicolon, or you are missing to do some of this checking. Okay, and then that's when you start having problems and things start not working as you expect. Okay, so that's why it's always good to start working from some examples, okay, and start changing them a little bit to adapt to what you want to do. So another example also that you can take a look at is this ray tracing. The concept is very simple. I have spheres, okay, and I have two tests. One is that I can test, use a very quick test to see if a ray is going to intersect a sphere or not, okay, and then once that I know that it intersects it, I can compute the value where it is intersecting it, and based on the value where it intersects the sphere, I can assign some coloring, okay, and that's what this part does. Here, basically, the main loop is just in this part, okay. I pass a given number of spheres. I can have several spheres, and basically for all the spheres, basically I need to check that the ray intersects. This ray is basically, if 1 pixel is going to intersect a given set of spheres, okay. And once that I detect that it intersects at least one of them, okay, then I can compute where it intersects it, an approximation, and color it based on that. So again, this is you spend actually more time you setting things up and parsing precisely where the variables are, and actually this is an OpenCL program. So yeah, we run this. All these defines basically they allow you to write programs that they are going to optimize based on the hardware that you are on which you are running this example. Here we run this, and let's say that my number of spheres is, let's say, just 100. Okay, I initialize all the values, and this is the result. Okay, but going from here, then I can just run it for more spheres. Okay, and as you can see, this is instantaneous because basically I'm using the 320 processors to compute basically this pixel by pixel, ray by ray. Something that is in the documentation in version 8 is this example, the Mandelbrot in 3D. you can take a look at the source code. Okay, and you can see that this is a program actually written by this person, David. Okay, basically this is an example that basically you can download it from the web, and it's very common that a lot of people, they just publish the actual CUDA kernel or OpenCL kernel. They don't publish how to move, how to transfer data and how to visualize any of that. So it's, this is a very convenient way that basically you can use programs that are available on the web or other people is distributing, okay? And then you can start very quickly prototyping them in Mathematica. I probably should have closed that one first. Yeah. Yeah. So it's doing all that computation basically in this on this image. Okay, and the size of the image is 480 by 640. Right. In the documentation, it's a very, very large documentation. Basically, it's quite complete in the sense that there is too much for some people. They have to read a lot. Okay, but it's very. It covers all the aspects. So everything that I presented here is just a minuscule part of what is present in the actual documentation. Yeah. So the first place to start with is you can always go to the CUDA link overview. Okay, and here they give you the introduction, how to set things up, which are built-in functions in Mathematica that already are using CUDA. Okay, and then some of the basis for programming, handling of memory, and some of these applications. And yeah, the source code for all of these is being provided in the system. How to handle multiple devices. Okay, yeah. So in general, it covers all those aspects. So with this, I conclude. So if there are any questions, okay, please feel free to ask us. Thank you very much.